All right, class, welcome to the second lecture in the thermodynamics portion of the course. And this lecture is going to focus around the state function of entropy. So when we were in Chem 111, we discussed enthalpy, which was also represented as delta H. And that had to do with heat energy, heat transfer, when we started talking about calorimetry, things of that nature. So now we are going to move into our next major thermodynamic parameter, which is entropy, and a lot of times that has to do with disorder or randomness in a system. So let's take a look at entropy here. So entropy is a thermodynamic state function which is going to examine the reversibility of a process. So remember, we were discussing reversibility a little bit in the last lecture. If you didn't fully complete that or understand that, I would encourage you to go back to the lecture on spontaneity, where we've discussed a lot of the sort of groundwork for this lecture. Okay, so it was originally defined as a reversible heat and temperature of a given system. So you can see down here, S is the letter that we're going to use to represent entropy. So delta S equals, remember Q from 111 represents the heat, and we're talking about specifically heat in the reversible sense, and that is over temperature, and that's how entropy was originally defined. Now there's many ways that we can go about defining entropy, and we're going to see some of those as we move along here. Okay, so entropy can easily be defined through statistical means, and a lot of times people will hear the term particle in a box, or you start talking about particles occupying certain locations or atoms occupying certain locations at a given time, and the probability models that the atoms will occupy a certain state, and that gets into statistical thermodynamics. Okay, so when we start talking about particles that can occupy these areas or boxes, we refer to any combination in which the particles can be arranged in that location or box as a microstate. So from an official definition, a microstate is a set of distributions that particles are going to be able to occupy. So you can kind of think of them as little containers or boxes or slots where you can put your colored particles, or you can use marbles if it helps you think of an example like this. And what are the different combinations that you can come up with? Almost like you're playing different odds or statistical games here. All right, so a visual example will certainly help us. So let's consider the distribution of 4 particles between 2 boxes. So we're going to have 4 individual particles and 2 boxes in which we can sort those particles. Okay, each combination is going to represent a potential microstate when we look at these probabilities. Now, I just want to mention, when I bring this up and we start working through some of this math, in the lecture series here, the bulk of the math or examples that I give are going to be pulled from your OpenStax textbook. Now, when we actually get into the face-to-face review time, when we sign on to do our actual class time with one another in the synchronous part of the course, we will be practicing additional problems that I've posted up on Canvas. But if you ever want to follow along with this, you can have OpenStax open at the same time. But my job is sort of to help clarify this and explain it as we're going along. All right? So here are the different combinations. We could take all 4 particles and put them in the left box, which would be similar, option A, to option E, which is where we take all 4 particles and put them in the right box. All right. Now, you can see when we start moving one particle, there's a couple options. We could move the red particle to the right, keep the other 3, the green particle to the right, keep the other 3, and so on and so forth as we're going along here. Now, when you get to C, where we have 2 particles of each, you can see that this represents the largest distribution or theoretical probability. And you can see here that when we're looking at it, it can make almost like a bell curve. So if I were to take a straight line and run it through the A through E, you could make a bell curve running perpendicular to that, with C being sort of the peak of that bell curve in the distribution. Okay? So every single one of these box distributions is going to be considered a microstate. So if we count that up, we've got 1 for A and E, then B and D each have 4, so that brings us to a total of 10, and then C has 6. So when we add that to the 10, that's a total of 16 possible arrangements that we have for the microstates there. All right, now we're going to break out the digital whiteboard in a second here and discuss some of this in a little bit more detail, because I want to take a look at the math behind this, and then we're also going to look at how we can calculate entropy directly related to microstate probabilities. And we're going to need something called the Boltzmann constant in order to accomplish that. So let's pull up the digital whiteboard and we'll do a little bit of math here. All right, so here we are, and we've pulled up the whiteboard. We're going to take a look at entropy calculations in relation to the microstate statistical model. So sticking with the same example, we have 4 particles in 2 boxes, and we said there were going to be a total of 16 different microstates that are scattered about this distribution here, right? Now, when you start working with this, you can easily determine the total number of microstates by keeping 2 factors in mind. And the first factor that you want to keep in mind is the number of particles. Now, your book, when it represents that, uses a capital N, and they say capital N is going to equal the number of particles that we're dealing with. Okay, now the other thing that's important to consider is the number of possible boxes that you can put these particles into or sort them into. And they use a little n for that, okay, and we'll just call that, for the sake of this example, number of boxes, right? But it's really the number of different spaces that these particles can occupy. And so we're just going to do some quick exponential math here. You can determine the number of microstates, and microstates is going to be abbreviated as capital W. So you can determine the number of microstates by setting it equal to little n raised to big N. So that is to say the number of boxes raised exponentially to the number of particles. And when you do that, you can find the total number of microstates. So in this example, we see that we have 4 as the number of particles. So big N is going to equal 4. And then small n would be the number of boxes. We gave ourselves 2 in this example. And so if we take 2 to the 4th, we end up with 16. And that's exactly the number of microstates that we would expect here. Okay? So when we have problems in the future, if you are given simply the number of particles and the number of boxes that you can sort them into, you should be able to come up with your microstates quickly. All right, now, a little bit more regarding this before we jump into the math with the Boltzmann constant. When the microstates have the same distribution, okay, so this is ignoring the particle identity, meaning the colors that we're assigning to the particles, you're going to get your distribution, all right? So option C has the largest statistical distribution, while options A and E have the smallest. But notice that A and E are being lumped in together. All right, so what this means is that the chance of the particles existing in the state of distribution C is going to be 6 out of 16. Now we can reduce that into 3/8. Okay? So that is the probability of the particles existing in that state, just from a counting numbers perspective. All right, now what's the chance of the particles existing all in one box? Well, that's going to be A as well as E. So in a case like that, you're talking about 1/16 up here plus 1/16 here. So if you add that together, you're going to get 2/16, and that's going to reduce to 1/8. So if we take a look, the chance of all the particles being isolated to one box is 1 out of 8, whereas the chance of them being in state C, 2 in each box, is 3 out of 8. So that means most of the time we would expect to find these particles in state C compared to state A or state E. Now this is very important because we're going to start tying this back into entropy in a moment, all right? But I want you to think back to the previous lecture where we were dealing with spontaneity. We had an example that was somewhat similar to this, where we were talking about all of the gas particles being in one side of a round flask, and then once the barrier is open to the empty round flask, the matter would equally distribute itself until it was approximately equal on both sides, and it would probably remain in that state for most of the time. And it was very unlikely that we would get all of the gas particles back on one side or another. Now, this is a minuscule example in comparison to reality. Okay, we're just talking about 4 particles in 2 boxes that we sort them in here. Okay, but what I want to point out here is that there's a smaller chance of them all clustering together versus them being spread out. So this statistically is going back to that sort of macro representation of the particles in the flasks and explaining why they would stay sort of equalized on both sides instead of all gathering on one side again. Now, is it possible that they could all gather on one side? Well, in a model like this, absolutely, because 1/8, statistically speaking, really isn't that small of a number. That's a pretty decent odd. But keep in mind, when we're talking about a mole of gas, you're not talking about 16, right? You're talking about numbers, okay, of 10 to the 23rd particles. So when we're dealing with small numbers like 2 to the 4th, okay, this is going to make it so that these extreme examples are possible. Now, when you start getting up to realistic numbers, like 10 to the 23rd, what is the chance that 10 to the 23rd particles are all going to end up in one box? It's going to be very, very unlikely, because then you're rapidly increasing the number of microstates that exist between these two extremes. And when you do that, you're rapidly building your distribution, and these tails of the distribution become less and less probable because you have to fill all that space in the middle. All right, so I know this is taking a minute, but I just really want you to understand the statistical portion of how we're dealing with this. All right, now let's tie this back into entropy, because that's what we're discussing here. So since entropy will increase logarithmically with the number of microstates, and we'll see that through math in a minute, the distribution with the highest probability, which in this case is going to be C, must also be the case with the largest entropy. So consider disorder, right? When we talked about solids and liquids and gases and how they're structured or ordered versus disordered, it is very ordered to keep all of your particles in one box. Then as you put one particle in the other box, you're becoming a little more disordered. And then option C has the most disorder, the most chaos. There's the most spread between all of it. And we can see as we rack up and accumulate all of these microstates under the C distribution. All right, so that means that option C will also be the case that has the most entropy. So we can relate this back to the example in the previous section with the flasks, because we can talk about the entropy is being very structured in that one flask where it's all contained, right? And then as it spreads out and these gas molecules are moving all about spontaneously, the entropy is increasing. So it's not as contained, it's spreading out, it's becoming a more disordered system. All right, so what about the math involved with this? So here's the math. The entropy microstate relationship is going to be S, where we're discussing entropy. Okay, now whenever you see delta, it's talking about a change in entropy. If you just see S, we're talking about entropy itself. Okay, so it's kind of a slight difference, because a change in entropy is still, the result is still entropy, but it's how much the entropy has changed by. So just keep that in mind if sometimes you see the delta sign and sometimes you don't. All right, so entropy equals K, which is the Boltzmann constant, times the natural log of the final number of microstates versus the initial number of microstates. All right, so when we deal with something like this, the Boltzmann constant is going to be equal to 1.38 times 10 to the negative 23rd joules per Kelvin. Okay, so this is known as the Boltzmann constant. Okay, and as we know from high school math and from Chem 111, a constant does not change. It's going to stay at that number, just like Avogadro's number or any others that we've come across in Chem 111. All right, now, ln is just the natural logarithm, and then W is microstate. So Wf is going to be final, Wi is going to be the initial. Okay, so there's a problem in your book And it says, what is the entropy change going from 1 microstate to 6 microstates? So we can solve that using what we had just outlined. All right, so now you're going to see a delta S here because we're talking about the change in entropy because we're going from one state to another. Okay, so delta S equals, and when I probably should have put a delta in front of this now that I'm thinking about it because we're talking about final and initial, so that is a change there. Okay, so delta S is going to equal the Boltzmann constant, 1.38 times 10 to the negative 23rd joules Kelvin. And just a quick reminder as we're going through here, try to remember your units whenever possible. It's very important. I know as we write it can start to wear down on us, but particularly at least in your answer, I would really make sure that you have your units in when you get to your final answer. It helps to keep track of it all the way along. All right. So the natural logarithm, and then we're going to have, it was the final, right, over the initial. So what's the final? It's going from 1 to 6. So 6 is the final number of microstates, and 1 is the initial number of microstates. Okay, so give you a minute to solve that. And for anybody that does not have a scientific calculator, you should have one for this course. You can go to calculator.net and you will be able to pull one up. Okay, so what I would suggest you do is just pause the video briefly if you wanted to calculate this yourself. If you're following along in your book, you can do that as well. So if you solve this, delta S is going to equal 2.47 times 10 to the negative 23, and that's joules Kelvin. Okay, because the microstates are unitless, so I just get a number back from the natural logarithm and I multiply that with the Boltzmann constant that has those units. So there we are, and delta S is going to be equal to this right here. All right, so hopefully everybody understands the math behind that. You can expect that when we practice in class as well as on exams, we will have material related to microstates. So make sure that you're feeling comfortable with this. And again, we will make sure that we go over some more of this in class. All right, so coming back to the lecture slides here, just to wrap it up. Okay, predicting the sign of entropy is also something that we want to be able to think about or have a good grasp on. So in general, we're going to be associating a positive value for delta S that will be involved with a more disordered system, and it's reflected with a higher number of microstates or possible particle locations. Okay, so when delta S is positive, we will associate that as an increase in entropy, and therefore the system will be more disordered, as we saw with the statistical model. All right, so when we have a delta S with a negative value, we're going to associate it with reducing the randomness. That means making the system more ordered. There will be fewer number of microstates that we can occupy. Now, this is going to be very important when we talk about the third law of thermodynamics. All right, so that will be in the next lecture, but I want you to keep in mind as you start to get into a perfect solid crystalline structure, you're reducing the movement and the kinetic energy of the molecules, and when you start locking them in, they have fewer and fewer microstates available. Okay, you're going to drop or plummet in terms of your entropy and disorderedness. Okay, so again, you can see the note here. We can apply this when discussing phase changes for matter. So we talked about this a little bit earlier in the previous lecture. I have a picture of dry ice down here, which is solid carbon dioxide that sublimes into gas carbon dioxide. So think about a solid, very structured, ordered, rigid, small amounts of movement going into a gas, very chaotic, random. Molecules have lots of space and can move all over. So that would be a situation where we would have an increase in entropy going from a solid to a gas. Okay, so entropy in the states of matter, you should probably have a pretty good grasp of this by now. Your crystalline solid moving to your liquid, we would expect that to be an increase in entropy, and we see that over the arrow, that delta S becomes greater than 0 in a case moving forward like that, right? And then as we move forward from a liquid to a gas, we expect that the change in entropy from liquid to gas is positive. But then when we go from a gas and we condensate into a liquid, now all of a sudden we have a negative change in entropy. Okay? And then, again, if we go from liquid and we freeze into a crystalline solid, it's a reduction in the entropy of the system. So then we talk about delta S being negative because the change is negative. It's becoming less entropy as we move towards that state, a less entropic state. Okay, so here's another graphic form, meaning literally a graph that you can see. So we've got entropy on the y-axis, temperature in Kelvin on the x-axis. And you can see what's happening to the entropy. All of these figures are coming from your book here. Okay, so we start out in the solid, right? We're starting to warm it. We're warming up the solid. And then suddenly we get into the phase shift and we melt. And right there at that temperature, we're melting, but we're increasing in entropy. And then we go. And we increase and we go. So what's happening is as temperature increases, and this should make sense, the entropy of the system is going to increase. And that makes sense because if we're talking about the way that phases are ordered or structured, and we say solid is going to be the fewest number of microstates, it has the least randomness, well, solids occur at lower temperatures, right? And then liquids occur at slightly higher temperatures, and gas states occur at the highest temperatures relative to each individual molecule. So, words of chaos, okay? As systems increase in temperature, as we just saw, and increase in the number of high energy particles, that means gases, right? As we're going through phase shifts, the entropy will increase. So what we're kind of getting at here, remember, we're not talking about any math after we left the microstate discussion. We're simply talking about, if I give you an equation, if I say that liquid water is boiled into steam, do you know whether the entropy is increasing or decreasing as a change? And you should be able to say it's increasing, but you should also be able to state why. Because the more ordered liquid water particles are now receiving more kinetic energy from the temperature increase. They're becoming more random and chaotic. They're spreading out more, and therefore we have more disorder. The entropy has increased. Okay, so up next will be the law of thermodynamics, and good for you if you know what this is previewing here. Hopefully most people do if they've been following the discussion and seeing where this is going to lead. So, until next time, I hope everybody has a good day, and I will see you over in the next lecture. Please remember to rewatch the first lecture on spontaneity if anything here was not clear. All right, guys, I will see you for the next one.